Hi guys, see you speaking again. Today we are dealing with RPM, revolutions per minute. Here we have a computer fan and it's just spinning. And here we have a display. It's a digital voltmeter, DVM. I picked up a diagram published years ago by K.H. Lawrence in Electronics. And don't worry, we're going to simplify this thing. The first interesting element in the diagram is this. This is a digital voltmeter and is saving me the time to build my own display. So, is this guy here. If you take a look on the bill, I just ordered from my favorite distributor. This guy here is a digital voltmeter, 200 millivolt. The model is less important because you can buy it from anywhere else, but this is the thing, 200 millivolt. Okay, so if I'm taking a look, I have a brand new right here, and this is exactly like the one I'm using, and it's coming with two little terminal blocks, 2 wire each, and is also coming with the cables attached. One terminal block, 2 wires, is for its own source of energy, which has to be different from the rest of the diagram. And the other 2 wires are for the signal you have to measure. Okay? So, again, you're looking on the box, and you look for the one which is 200 millivolt. Not 100, not 50 millivolts, 200 millivolt, the range. Okay? Regardless the model. So far, so good. Very good. So now, talking about the fans. You see this one here, the model is company ARX, and the model number is right here, FD2080, FD1280. What the manufacturer tells you right away is the voltage, this is 12 volt, is recovered from a computer, still has some dust on it, and 0.2 amps. Because, of course, it needs a source of energy, so you have to know what is the consumption of that fan. And they also give you the CFM, which stands for cubic feet per minute. So how many cubic feet it is able to remove out of your box every minute and replacing it with fresh air. But for me, it's difficult to measure the CFM, and I'd like to measure the RPM. Excepting when I'm going to look for that particular model, let's say, to look for the speed, it's very difficult to find it. So this is why we are going to measure it. So, talking about PC fans, let's say, roughly speaking, all of them, they have something in common. And what do they have in common is that the kind of the motor inside the fan, it's a brushless motor. Good news is the first word, brushless. It doesn't have brushes. This is why these fans are really quiet compared to a standard DC motor. But on the other hand, the brushless motors, even if they are called DC, because it's given here, DC 12 volt, they are actually driven by some transistors inside that little enclosure, because you have to create the phases for that motor to spin out. And because of this, another thing they have in common, of course, they have a polarity. So anytime if I pick up a simpler one, this one only has 2 wires, there is a red and the black one. The red is the positive, the black is the negative. So you have to consider that polarity, because otherwise you won't turn. Why? You don't energize directly the motor, you actually energize the transistors driving the motor. Very well. So now, let's talk a bit how can we quickly classify these fans? I'm not talking about voltages, because you can classify them depending on the voltage used to make them spinning. I'm not classifying using the amperage. I'm simply classifying using the number of wires. So let's come closer here, and we are going to have 2-wire fans, exactly like this one. When the fan only has 2 wires, the only thing you can do, you put the power over these 2 wires, and then it's going to spin at the nominal RPM, and there's nothing else. Now, 3-wire fans, and by the way, this one has the 2 wires, the red and the black, because the red is for positive, the black is for negative. Very easy. But then I have this one here. This one has 3 wires. So of course it has the red and the black, but it has additionally, so the red and the black, which are positive and negative. But then it has a white wire. And if this white wire is present, it's because using this white wire, you can read information about the fan speed. So it has inside some sensors which are able to feel the magnetical field, the Hall effect sensors, and by using this white wire, you can use to read RPM. So you use a tachometer. That's exactly what we're going to build. But we won't use this wire here, okay? And the third kind of fan is going to be one like this one, right here, which has 4 wires, not only 3. So this one has 4-wire fan or fans. 2-wire, 3-wire, this is 4-wire. It has the red for the positive, it has the black for the negative, it has the white for the tachometer, okay, and it has a 4th one which is blue. And if they are provided with the blue wire, then you can adjust the speed of the fan. So, speed control. There are several methods to control the speed of a fan. It's not the purpose for today's video. But the only kind of fans you can use to easily control the speed are the ones having the 4th wire, because otherwise, for the other fans, is not that easy to control the speed, but only usually modifying the voltage. For example, a 12-volt fan is going to start spinning at about 7-8 volts. You cannot lower it below 7 volts. Okay? Very good. So now we know there are 3 kinds of fans, 2, 3, and 4 wires. But even for the 3 or the 4-wire fans, if you only use the 2 wires for the power, the red and the black, you can make them spinning at full speed, the nominal speed. So now, the purpose is, how do we build such a diagram? And the diagram we're going to build is going to be with no contact, so there is no mechanical or physical contact between the fan and the diagram, as you can see. I can remove it anytime, it's not touching physically anything in my diagram, simply because the diagram contains, as the most important element here, an optocoupler. It's an emitter right here, this white guy, and the receiver over here, the black one. So if I'm taking a look, I have some right here in a bag. These white ones are some infrared diodes, exactly like LEDs, but they emit the light in frequencies below of what we can perceive. Our eyes can't see this, because if you take a look here, we can't see any light between the two, okay? They are infrared. So this model I chose, LTR3208, is the diode emitting light. And on the other side, we have this little black guy, which is here. The model I chose is QSD123. These are phototransistors. And the reason they are black is because the manufacturer wanted to minimize the influence of the light around over the phototransistor. And it also has a narrow angle to catch the light, a narrow angle, about 24 degrees. So this is a 24-degree narrow angle phototransistor, and this is a kind of equivalent to the LED, but is not emitting light in the visible spectrum, it's emitting light in infrared. So anything you put between, if you watch here the red LED, the big LED, anytime I put my finger between, if I hold it, there is no light passing by, so the LED goes on. If the light can pass between, the LED goes off. So anytime I have a pulse, this red LED is going to see it, okay? So this is how the optocoupler is working. So now, let's see how do we build that diagram step by step. My problem is, if I take a look at the fan, it's something interesting. I want to measure how many times the fan is turning per minute. But actually, how do I do it per minute? I measure how many times per second, and then I multiply times 60, and I get how many per minute. For instance, if this one is spinning 50 times per second, 50 times 60 seconds is 3000 RPM. So the number I'm going to see here is going to be close to 3000. Okay? So let's see this one again. So this one is spinning, let's say, is going to stabilize a bit higher. But if you use 1800, it's 30 revolutions per second, because 30 per second times 60 is 1800. So here, if I want to read that number, I forget about the decimal point and I put one more zero at the end. So now it's going closer to 1900 RPM, because it's 1880, 1890, 1880. The last digit is not even relevant, because there is no big difference if it is 1891 or 1892, okay? So 1890 approximately, okay? This is the RPM at this moment. Good. But now let's see. I'm going to present you the diagram in several stages to make it easy to understand. And this is going to be the setup before, in another video, we're going to be able to transfer the components from the breadboard to a more stable arrangement, like on a printed board, okay? So for that purpose, I'm going to use here several diagrams. So I'm going to start with this one. That's a very simple diagram, and it has nothing to do with the display we were seeing before, okay? What we were seeing before the display, this is the last part of our project. But what we have to build first is what is a counter. This package 74193, it can be found in different forms. I'm using a CMOS one, which is 40193, but the function is absolutely similar. And what's the point of using a counter? Why do I need to use a counter? Take a look why. Because here I have this fan, and I want to measure how many times it's spinning per second. Yes, then I'm gonna multiply times 60, is another story. But how many times per second? But you see here, this one, if you take a look at the propeller, it has 1, 2, 3, 4, 5, 6, 7 blades. So during one revolution, I'm gonna have 7 blades, each of them cutting the beam right here between my diode and my phototransistor. So actually I'm gonna get 7 pulses. But I don't need to measure 7 pulses over my voltmeter. I only need to measure 1 pulse, 1 revolution. I want to count the revolutions per second or per minute. I don't want to count the number of blades. For that reason, I'm going to use a counter like this one. And after I make it working, I'm going to make it in such a way that it gives an output every time I'm going to have 7 blades. So before being able to measure the blades, we have to make sure this thing is working. And what I put in red here, these elements in red are only for the troubleshooting, because I want to build a project at the same time doing the troubleshooting. Otherwise, if you take a look at all the wiring here, chances are you're going to do mistakes. Everybody does, including myself. So we have to minimize the chances for mistakes by doing what? Providing things for troubleshooting. So for a counter like this one, instead of using from the beginning the optocoupler made by my diode and phototransistor, I'm going to use something classical, which is a, you can hear it, a micro switch. And by pushing the micro switch, I'm going to be able to keep counting my counter. So this is the micro switch controlled by 2 gates, because I have to debounce the micro switch. So the signals from the micro switch debouncer are going to enter here. My counter is counting up. By the way, the fans are spinning one direction. They don't spin both directions. How do you know what is the direction? Sometimes, and this is a good information from the manufacturers, they show it to you somewhere here in the top with the arrow saying what direction the flow goes. But some other times, it's very difficult to find this arrow, okay, placed on the fan, okay? Like on this one, it's not even visible. How do you know what direction the flow goes? You take a look here on the label. So as soon as you see the label, this is the direction the flow goes. Here is the propeller. It doesn't go that direction. It goes the opposite one, this way, okay? So if I'm energizing it, just for a second again, you're going to take a look. You see? This is the direction it's pushed, not this one. Here is catching the paper, okay? Here is pushing. So that's how you know what is the direction it's pushing. So far, so good. Okay, so now we know the direction, but it's only one direction. This is why, even if this is a versatile counter, which is able to count either up or down, I don't use the down one. So I move the down to the plus 5 volts. So it's going to stay there. It's not bothering me. It's only counting up. But what I want to do, I want to check the counter counting properly. But this is a binary counter. So for the binary counter, it's going to have 16 positions, 0, 1, 2, 3, up to 15. And they are not expressed in digital like here. They are expressed in binary on 4 LEDs. The 4 LEDs are right here. So I'm going to make it in such a way that instead of receiving the signal to count from the optocoupler, from the phototransistor, to make it receiving the pulses to count from my micro switch. So I'm going to move the wire on the pin number 5, which is counting up. Okay. Okay, just a second. Right now. Okay. So now, if you're just watching the 4 LEDs here, I'm going to pass over a full cycle. Good. So now, because I want to count it, I'm going to also disconnect the reset of my counter. And the reset of my counter, instead of coming from the rest of the circuit, is going to be simply disconnected. So now, let me just do a full cycle. Right now, when all the 4 LEDs are off, that's a 0. Then I have 1. Next is 2. This is 3. This is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And if I press it one more time, it goes back to 0. Okay? So anytime I do it, I'm going to get a pulse here. 4, 5, 6, 7. See? 8, 9, 10, 11, 12, 13, 14, 15, and back to 0. So that's how I know my counter is operating properly. Okay? Now, when my counter is operating properly, this is the first stage of my project. I put it away, and now I'm bringing the next stage. What's going to be the difference between the two stages? If I'm showing you both of them, okay? The first stage right here is just counting 0 to 15. I actually don't need that. I actually need to build a little, let's call it a decoder, stopping my counter at 7. So anytime I receive 7 pulses, because the 7 blades are going to pass here in front of the phototransistor, every time I'm going to get 7 pulses, my counter is going to deliver out to be counted by my digital voltmeter only 1. But I noticed something even more interesting. And this thing is, there are two kinds of fans I found. This one, for instance, it has 7 blades. But there are others only having 5 blades. So we have a dilemma. What we are going to count? Are we going to count 7 blades or 5 blades? So what did I do? I didn't find computer fans having 3, 4, 6, or 9 blades. I only found some having 5 or 7 blades. So I modified my decoder in such a way that it is able, by just moving a jumper, this little guy right here, now is put on the position for 7 blades. And this is here on my diagram for 7 blades. And if I move the jumper in the other position, it's going to be able to count 5 blades. So what's going to happen? What's going to happen is, when I'm going to push my micro switch, instead of counting like here to 15, because now when all the 4 LEDs are on, this is 15, it has to only count to 7, like here, or if I move the jumper in the other position, to 5. So let's find out how do I do that. So I'm going to move now my reset. I'm going to move now my reset from the ground where it was before to this pin 8 of a gate with 4 inputs, of an AND with 4 inputs. And by doing this, this decoder, which is now connected over 7 blades, you take a look here when I count with the same micro switch, 0, 1, 2, 3, 4, 5, 6, and when I'm going to press the next time, it's going to go back to 0. Take a look. 0, because all of them are off. So it's counting 0, 1, 2, 3, 4, 5, 6 pulses, and the 7th goes back to 0. Now I'm going to move the jumper. I'm going to move the jumper, putting it opposite way, like this. And guess what? It's going to count 5 positions. 0 is the first position. 1, 2, 3, 4, and next time it's going back to 0. So this is going to be for a fan with 5 blades. And when I move this one here, opposite way, like this, it's going to be for a fan with 7 blades. 0, 1, 2, 3, 4, 5, 6, and back to 0. So that's how I'm going to do. This is why I need the counter to use, because by building a decoder here, I can use either fans with 7 blades or fans with 5 blades. Let's check it out. This one here is the one with 7 blades. I'm going to connect it. Okay. So this one here, if I move this one back, okay, is going to count the RPM, okay? So, in that moment here, I have my whole diagram working fine. Let's go for the next stage. Now, if I compare this diagram versus that one here, the only difference is here in the new one, I'm gonna have an option. I can pick up signals either from my micro switch, or that's what I was doing with this wire right here, or I can connect the source of the signals from the little diagram with the phototransistor. Okay, so this little diagram is the classical one, which is just amplifying and cleaning the signal coming from the phototransistor to be used by the counter. So this one here, how do I check it? The little diagram using the phototransistor, very easy to check. Again, I put my finger here, and now take a look at the 4 LEDs. 2, 3, 4, 5, 6, and next one, back to 0. It's telling me that now the diagram is connected for a fan having 7 blades. Again, 1, 2, 3, 4, 5, 6, and 7. And anytime I have a signal, I see the big red LED going on. And these ones here, only 0, 1, 2, 3, 4, 5, 6, 7, and 0, 1, 2, 3, 4, 5, 6, and the next one, 0. And the thing about troubleshooting is, as you can see, when you count 0 to 7, the fourth one should remain off all the time. And that's how you know you're right, okay? Because when the full counter is working, it should be 0 to 15. But the fourth LED right here, this one only goes on if the numbers are bigger than 7, okay? Up to 7, you only have to see the first 3 ones. And I'm going to put this one again at work, like this. And I'm going to energize, okay? You can see the 3 of them flickering, but not the fourth one, because everything goes 0 to 7. If I do the mistake, to move it for 5 blades, like this, I move it for 5 blades. But my fan has 7 blades, and I wrongly measure the speed. Of course, it's going to show me a much higher speed, because I have pulses every 5 blades, but my fan has 7. So for that reason, I have to be careful to have a correspondence between the number of blades I'm counting, so the position of my jumper, and the real number of blades of this one. So I'm picking the other one, this one with 5 blades, because right now my switch is on, my jumper is on 5 blades. And I'm going to connect this one. And again, you are going to have a lot of trouble to find the actual RPM in the specs for such a fan. I repeat, you have to consider the polarity of the fan, okay? So red to red and black to black, okay? So doesn't want to enter. Okay. Okay, so now this is a very strong fan, and for this one I found somewhere the speed to be somewhere around 4200, and it's a strong one. You can hear it, and if I place it right here, take a look what I measure. It's almost 4600 RPM. Okay, it's 40. This is the real RPM, 4600. Okay, and the fan is very strong. Okay? But this is 5 blades. Okay, so then I'm disconnecting this one. And just for a second, if I connect my other fan again, and I'm making it spinning, because this one has a much lower RPM, I can even leave it on place. Okay. Now, if I connect for a second the third wire, because this is a 3-wire fan, okay, and I'm going to connect the third wire right here, I can notice right here on the oscilloscope, I can even see some pulses over the oscilloscope. As you can see, the pulses are not extremely clean. I have to clean them out. And these pulses are coming from inside the fan where there are the Hall effect sensors. But please be careful, because there are 2 Hall effect sensors inside. So whatever I'm going to measure using the signals coming on my oscilloscope, it has to be eventually split in 2 in order to find and to process the speed. Okay? That's not the information I'm using right now. Why? Because not all the fans have 3 wires. There are a lot of fans having 2 wires, so they don't give me a signal to measure later on, either with the oscilloscope or with the tachometer. Okay? So for that reason, I built that little project to measure the speed of a fan, regardless the number of wires. Okay? Good. So now I found that the third stage was containing the 2 sources of signal. So there was one source of signal from a potential source of signal from the micro switch, and another source of signal from the input stage with the phototransistor and the LED. Now, this is what I built. And from the pin 6 of my counter, so after each 7 or 5 pulses, depending how my jumper is positioned, I'm picking up the signal on this blue wire here, and I'm bringing it right here at the input of that voltmeter project I took from the Electro magazine, published already by K.H. Lawrence. And if you remember, take a look, the original diagram and the new one. This is much simpler, because I don't need this part here. This is only used for the calibration of my voltmeter. And later on, when we're going to pick up the parts and put them on a printed board from the breadboard, then we're going to talk about calibration. And we won't need this one here. We're going to use a function generator for that. But right now, I eliminated what I didn't need. And another note is the original voltmeter they used, it was energized at 9 volt. And this is why they had here a stage, which is a voltage regulator from a 9 volt source to lower it to 5. So as I don't need it, why I don't need it? Because the voltmeter I found is 5 volt energized. Okay? So this one here, it says here, power DC 5 volt. So my voltmeter, this one here, is going directly working at 5 volt. I don't need 9. Okay? For that reason, I can simplify. It remains here with the separate power supply. I'm using this one right now. And all the rest of the diagram is energized directly 5 volts, so I don't need here the block with the voltage regulator. So the signal enters right here on this capacitor over here. So this white wire comes from my pin number 6 and the LED, the third LED, and it's coming right here to count the pulses. Okay. One little element I can notice on the diagram is this little black guy, which is over here. and is not very relevant for you right now, simply because we don't have everything embedded in a box where we need to control the temperature. So if you don't need the thermistor, this one here, the NTC, then we can eliminate it from the diagram. I left it here anyway, but I wanted you to see how does it look like, okay? That's a thermistor. At the room temperature, it has about 10 kilo ohm, and the resistance inside, it's going lower and lower as the temperature goes higher and higher. So this is the element, okay? But the rest is pretty easy to do on the breadboard. The last thing we are going to do is to compare this diagram versus the final one. And the final one, if you take a look, what I put in red, the micro switch plus the debouncer, and the 4 LEDs to monitor the counting of my counter, I removed them from here, okay? Because in the normal functioning, you don't need them. When do you need these guys? You only need them when you do troubleshooting, okay? Once the troubleshooting is done, you can remove them, okay? So this is going to be the final diagram here with the main control elements, okay? So here is the jumper, which is going to remain only connected to the phototransistor. Anytime you need to put it on the test down, you have to connect the micro switch. Here, we don't use the bottom side of the jumper because this is going to be another time when we talk about how to transfer it from a breadboard to a printed board, how to do the calibration of our voltmeter. This is here when we are testing the counter. If we put the reset or the clear of the counter to the ground, then we can count 0 to 15. When you connect it in a normal position right here, it's connected to the decoder. So the decoder is going to make the counter reset when it receives either 5 pulses if our fan has 5 blades, or from 7 pulses if our fan has 7 blades. Okay? So these are the elements to control, and you're going to find all these in a folder on Google Drive. Okay? So this is going to be our final diagram, which is much easier to understand and simpler than the original one. Okay? So far, so good. So the last thing we do, we're going to measure the speed of some fans. Okay? This one here is a fan having only 2 wires. You'll be very careful because anytime you connect them, the fan can start jumping. It creates a lot of air pressure. So you'll be very careful when you connect the fans. Okay? So this is why when I connect the fans, I have my power for the fan disconnected. Okay? So I connect this one here. I position it over here on my optical reader, and then I'm going to energize the fan like this. And I'm going to read the speed, which is now 2800 RPM. Okay? This is one. I remove it. I disconnect. I pick up another one. This one is a very strong fan. I expected to have a very high speed. I found the speed for this fan. It should be around 5800. I don't know. We're gonna measure. Okay. But you'll be very careful because the power for the fan has to be first disconnected. Otherwise, you're gonna be in trouble because the fan is going to jump all over the place. Okay. So you hold it. You energize. Can you hear it? It's a very strong one, okay? So now I'm just placing it inside. And because I hit the diode, okay, I have to place it back. You see the speed is 5400 RPM, 5440. Is not far from the one I found on the internet. So it should be the good one, okay? But again, that's a very strong fan and I don't have a lot of room. Okay, you have to leave enough room on the breadboard. And of course, if you hit one of your diodes here, you have to replace it back in the good position. Okay. And I have a very small one here. This, because it's so small, is also energized at 12 volt, but it has to move very fast in order to displace some air. Okay. And for that reason, you're going to see what speed it has, okay? So we're going to connect the two wires for the power. Remember, you have to consider the polarity. So then, if I'm connecting it over the power supply, the red and the black on the negative, I'm holding it, and then I want to give it power. Take a look what happens. It's spinning, and I find the position where I can read. Take a look at the speed. It's a very high speed. Okay? Why it shows so high? It shows so high because the fan I was measuring before was having 5 blades, but this one has 7 blades. So I count again. 7 blades over here, and my switch has to be removed and put the other way to measure 7 blades. So now when I measure 7 blades and I put it over here, so the speed is around 6,800 to up to 7,000. You just have to find the right position because there's not much room to read it. Now it's okay. See? So that's the speed. Okay? Just let me find it. That's the position. Okay? 7,000 RPM. Okay? 7,000 RPM. If I stop it, it's exactly what I found before. Okay? Good. So this is how we measure the RPM. And this is how we use our diagram to build it, to do the job. Thank you very much, guys. See you next time for the next one. Bye-bye.